Okay. Yes, so I'm James. Thank you so much for coming today. Today I'm going to be talking about benchmarking YOLOv5 across high-powered cloud GPUs on Paperspace. If you are not familiar with us, Paperspace Gradient is a platform for building and scaling machine learning applications. You could explore a new library or dataset in a notebook, automate pre-processing, training, or testing with a workflow, and then bring your application to life with a deployment. I would love for all of you to join our community of over 500,000 users on Gradient after this call. But today we're going to be using the platform as our demonstration space. So just to give a little bit of an overview about what we're going to be covering, we'll start with a kind of a broad strokes overview about understanding GPU hardware for training YOLOv5, specifically talking about terminology that I believe you should know, and NVIDIA microarchitectures. We will then move on to talking about the advantages of newer GPU technology for training YOLOv5 before looking at the benchmark demo and code walkthrough. We will then compare our results and excuse me, we'll then compare our results for the benchmark and then close with some tips for choosing the right GPU for training your own custom YOLOv5 model. All right. Give me 2 seconds, please. All right, first. So the first thing when understanding GPU hardware for training YOLOv5 is to understand some of the relevant terminology. In particular, I want to bring attention to VRAM, which is the GPU short-term memory, and it determines how much of the total data that can be processed at a given time by the machine. The throughput, which is the measure of the data transfer speed between the GPU and the system across the bus, which influences how quickly processing can take place. CUDA cores, which are the floating point units in NVIDIA graphic cards that correspond directly to throughput, the amount of CUDA cores, I should say. Tensor cores, these are the technology that enable mixed precision computing and dynamically adapting calculations to accelerate throughput while preserving accuracy. Ray tracing cores, or RT cores, are accelerator units that are dedicated to performing ray tracing operations. And computer number format compatibility, which is the internal representation of numeric values in a digital device, is hardware or software. Most GPUs give the ability to work with full precision 32, FP32, I should say, which is a measure of the number of flops or floating point operations per second possible with the GPU at that format, and half precision, FP16. And then there's also the situation where you would want to use those together, as I mentioned before, in mixed precision, and do the calculations with multiple number formats in one computational workload. Next, I want to just briefly introduce some of the microarchitectures for the GPUs that we're going to be talking about today. The microarchitecture corresponds to the generation of the NVIDIA GPU's development, and each successive round of development leads to corresponding advances in their capabilities. So there are kind of two classifications for these GPUs. They are namely the workstation, or the desktop workstation, I should say, and the data center, formerly known as Tesla GPUs. In the first category, we have examples today from Maxwell, which was introduced in 2014. And at that generation, introduced a new streaming multiprocessor to accelerate processing. Then Pascal, this is both a workstation and data center GPU series, but we're only going to be working with the P4000, which is a workstation today. These were the first GPUs with NVLink, which is really useful for scaling applications across multiple GPUs. And finally, Turing, which in 2018 introduced ray tracing cores. Then for the data center GPUs, we have Volta, which added second generation NVLink, and Ampere, which is the most recent, still publicly accessible GPUs. There is the newly announced Hopper as well. And Ampere added next generation tensor and ray tracing cores, third generation NVLink, and multi-instance GPU, or MIG. And we can see, if we look over here on the right in this example, just how much of a difference this generation to generation development actually makes. The A100, admittedly, it has eight more gigabytes of VRAM than the V100 used for the sample, but that still experienced up to a 6 times speed up with full precision BERT large training in their test. Excuse me. All right. Slide. So now that we know a little bit more about these NVIDIA GPUs, let's talk about some of the advantages of the newer GPU technology for training models like YOLOv5. I mentioned tensor cores a moment ago. These use mixed precision training to accelerate processing with integrated FP32 and FP16 format training with minimal performance loss. This is an extremely useful technique, and we want to apply it wherever possible. Ray tracing cores take this a step further, and actually YOLOv5 has integration with TensorRT to use these ray tracing cores to accelerate processing. Structural sparsity, this is a feature of Ampere GPUs. YOLOv5 models can have millions of parameters. Our demo today, for example, has 86 plus million, and new GPUs can use artificial sparsity to accelerate training and inference across these. And finally, NVLink, which I mentioned also in the previous slide, is a technology for accelerated parallelization of training across multi-GPUs. This is improved with each generation of microarchitecture and is insanely useful when working on multi-GPU machines. And then over here on the left, I have a little GIF showing how tensor cores can accelerate processing against different computer number formats. There's int8 and int4 here, which I haven't mentioned. These are even smaller than the floating point 16. And when using int4, Turing tensor cores, which aren't even the newest generation, experienced up to a 64 times increase on the processing. Okay, well, that is enough talking about the hardware. Let's get into the actual benchmarking task. So for this benchmarking task, we trained a YOLOv5 model across 6 different machine types. These were namely the M4000 with 8 gigabytes of VRAM, the P4000 also with 8 gigabytes, the RTX 4000 with 8 gigabytes, the A4000 with 16 gigabytes, the V100 with 32 gigabytes, and the A100 with 80 gigabytes. These were all trained for 20 epochs for the initial benchmark, and then we took 2 of those machines, the A4000 and A100, and trained those for an additional 100 and 250 epochs. And all of this training was done on a dataset called the Aerial Sheep dataset. This is one of the official datasets you can get from Roboflow Universe. Roboflow is wonderful if you haven't used them. But per the official description, the Aerial Sheep dataset contains 1,727 images taken from a bird's eye view with instances of sheep in them. The images do not differentiate between gender or breed of the sheep and instead group them into a single classification called sheep. And I chose this dataset for the ease of replication of training across the highly variable power that we are going to be having in these GPUs. This is a data set that we could do training on with the very relatively weak M4000 and the extremely powerful A100. So after these benchmarks were complete, we compared the results for their training times and found the optimal GPUs for each task. And then we're going to attempt to show how different GPUs can be cost effective for different levels of computational expense when training YOLOv5 by comparing how these values change as we extend the number of training epochs we are going to have. Okay, so now I would like to just briefly show the web page for the data set as well as the notebook I use. So here's the Aerial Sheep data set, and here's a sample photo from there. I had a picture in the slide just now, but that's from my model training. I figured this would be better to give you an idea of what these images all look like. They're fields with labeled sheep. Pretty simple. And here is the notebook. I will actually throw a link to this in the chat right now so that if anybody wants to ever recreate this or follow along, they can. Oh, sorry, sent that to the hosts and panelists. Oh, Paula, if you could share that with everyone somehow. I'm only able to send to post.
Sure. Yeah, I'll change the settings.
Thank you so much. Okay. So this is my workflow. The nice thing about the Gradient notebook we're working in is that it comes pre-installed with all the packages I needed to run YOLOv5. This is just the standard base container we have. So the only thing I needed to do to actually run this was to install Roboflow and get my data on here. Roboflow provides a really nice just output that you can copy and paste in here to do that, which I used. I've edited a little bit, removing my API key, and there was actually a bit saying to download it here in YOLOv5 format. So if you wanted to recreate this on your own, just keep in mind that you may need to go back to the Arial sheet dataset and do that yourself. Then next I have these cells. This is where I have my model training for 4 of the different sets of training that I ran. In particular, there is the RTX 4020 epoch training, the A100 100 epoch training, and the A100 250 epoch training. Then down here we have just some quick data exploration, including a data frame and some plots, which I will go over in just a moment. So feel free to look through these on your own if you would like to recreate them. It's a worthwhile experiment if you would like to get a more hands-on means of understanding how your GPU can affect these training times and in turn the cost effectiveness of training your model on that GPU. Okay, let's go back to the slides. And I mentioned this a moment ago. These are the predictions from the YOLOv5 training, and it's the way that they actually show the labels makes it kind of hard to discern what's really going on there. But it's using the same images of the sheep without their labels and applying them on. Typical YOLO workflow. Okay. So let's look at our first results for 20 epochs. This was the experiment that I did across all of the different machines. And I wanted to see if I could find a relationship between the type of GPU and the time it took for training, just on a really broad, big level. And I was able to show that, in particular, that there is something going on with like the age of the GPU, the generation, the VRAM, and the CUDA cores, and the corresponding length of time it took to do training. Notably, there was a significant speed up between the P4000 and RTX 4000 training, which shows you how important the introduction of those tensor cores was. You can see it's going from 18,907 to 3522 seconds. That's almost 6 times speed up with a machine that has the exact same amount of RAM. Then we can also look at the M4000's comparatively long training time, and we can see that the relative lack of CUDA cores, and this is something you would need to look up outside of this session, but the M4000 has significantly less CUDA cores than the other examples we're using here. I believe it's around 200. Without those CUDA cores, its throughput is significantly lower than the other GPUs with the same RAM, the RTX 4000 and the P4000. Then the highest or best performing were the A100 and B100, which had significantly more RAM than the others. Not a huge surprise. We can clearly see that the fastest GPUs were the most powerful and advanced data center GPUs. But how does this really measure up when we introduce the factor of cost? How does this change our consideration? Well, I've got 2 plots here that I made from breaking out the same information in terms of pricing. On the left, we have a graph just showing the hourly costs for each of the GPUs. So the M4000 costs 45 cents. I want to note that the M4000 is actually free on Gradient. This is our core pricing. So if you wanted to use a desktop GPU, we also offer those from our core product, and this is how much it costs to use the M4000 on it. The P4000 at 51 cents, the RTX 4000 at 56 cents, the A4000 at 76, the V100, a big jump up to $2.30, and the A100 at $3.18. Then on the right, we have a similar graph to the one we had on the last page, but showing the relationship between that training cost and the price for 20 epochs. Excuse me. Sorry. As we can see, we can start to infer a bit of a story here from this data. The oldest generations of GPUs, namely the M4000 and P4000, are significantly more costly than the other options. So $4.96 total cost and 268 cents total cost. Sorry. This is despite the fact that they have the lowest per hour cost, and it tells us a lot about how using a more modern GPU with more modern technology within can speed up our training significantly and thus have a very significant effect on our cost benefit of running on that machine. Then the more recent workstation GPUs, these are the RTX 4000 and A4000, offer the lowest training cost for a comparatively fast training. If we go back to the previous slide, we can see that the A4000 is only about 700 seconds more than the V100 at half that RAM. That's very impressive. So these immediately stand out as a really, really nice choice for this length of training. And then the most powerful examples, which are the data center V100 and A100, cost around twice as much as those workstations did to run this task at about $1.11 and $1.05 total cost to run. So what does this tell us? When you're training YOLOv5 on this relatively small data set, it's worth mentioning that the original data set was 1,703, I believe, images around there. Then when you use Roboflow, you have the option of applying various transformations like adding noise, rotating an image, etc. And on the free plan, you can triplicate your data set size. So our data set actually was around 3,609 training images. So when training YOLOv5 on this relatively small data set for a low number of epochs, we can see that the best choice in terms of cost comes from these newer iterations of the workstation GPUs, the Turing and Ampere workstation GPUs. These desktop GPUs intersect at the lowest values in terms of power and cost, with the A4000 in particular, with its 16 gigabytes of RAM, really excelling. We can infer that from this that any YOLO training task with a relatively low compute need can be efficiently completed on a workstation GPU like this. And additionally, we can infer that this would be sufficient for tasks like fine-tuning or using a smaller data set to update a model after initial training has already been completed. To the point that the power of a data center GPU like the A100 is outweighed by the cost to run it. With this in mind, we need to then consider why would somebody use the more expensive A100 then? Well, it gets down to expense, and there's two ways we can add expense to our task here, which is either to expand our data set size or the size of the actual images themselves, or to lengthen the training. So we're going to add our computational expense by lengthening the training and look at the same exact training task for the A4000, which was our best performing GPU, and the A100 at 100 and 250 epochs. While this won't have a significant impact on the precision of the model, which is why we have so far not really mentioned this, we can still use this modified task to see how the expense will affect the selection of the best model for the task in terms of cost. Okay. So here we have the results for benchmarking YOLOv5 for at 100 epochs. As we would expect to see, the A100 trained YOLOv5 for the length of time much more quickly than the A4000. This was about 3.38 hours versus 1.27 hours. If cost was conserved though, then we would expect when we scale our task from 20 to 100, that our final cost of training to increase 5-fold for both GPU tasks. In practice, or in reality, this was the case for the A4000 in our experimentation, but the A100's cost was only about 4 times that of the 20 epoch training. So going from the, looking in the previous slide, going from that 0.51 and 1.05, we would expect 2.55, which is very close to our 2.57, and 1.05 to go up to 5.25, which is significantly higher than 4.04 for the purposes of our experimentation. We can thus infer that this gap in price is starting to narrow as the overall computational expense of the task increases. Let's take this further with the 250 epochs experiment. Sorry, one moment. Yeah, as we continue our experiment, we can see that the training costs begin to converge as the computational expense increases. Here I've got a plot on the right showing the cost for the 2 different GPUs over time for the this task. The orange is the A100, the blue is the A4000. I apologize, I should have labeled those in hindsight. And the values above them are the cost values labeled. We can see that here, this was almost, or actually over double the cost, then it's shrinking down significantly and narrowing even further as training goes on. At this current rate, according to my own calculations, they should intersect after about 348 epochs. It would likely be even lower, judging by how the trend in the slope of the lines are changing. The A100 is flattening out more, while the A4000 is staying rather consistent. But we can still take away quite a bit from this. It shows very clearly that while workstation GPUs like the A4000 are evidently cheaper for shorter training sessions or using smaller data sets, like when updating or fine-tuning a model, as I said before, data center GPUs like the A100 prove more cost-effective for long, computationally expensive training tasks. So with that, I think it is pretty clear to say that if you were going to be training YOLOv5 on one of these NVIDIA GPUs, and it is my recommendation that you use at least one of the ones mentioned in this talk. They're all really nice. It would be my recommendation that you use the A4000 when you're working on something a little less computationally expensive, like, as I said before, fine-tuning or updating a model. And something like an A100 would prove a lot more cost-effective in the long run for computationally expensive training tasks. And let's elaborate a little bit on that. So when selecting a GPU for training YOLOv5, the primary consideration should be around how large your data set is, how quickly you need to train your model, and how accurate you need the model to be with its predictions. So first was data set size. A workstation GPU like the A4000, we've shown today it is more than sufficient for small data set training of YOLOv5. Like the 1,727 images, which of course bumped up to, I believe it was 3,609, I said. Yeah. But once your data set pushes past that, which will happen with the recommended 1,500 images per class, this is from the Ultralytics YOLOv5 docs, then a GPU, a data center GPU like the A100 would be more appropriate. If we need to consider speed, like how long the training needs to be, relatively short training sessions with few epochs will likely not need all the power of a data center GPU, like when we're fine-tuning to update a model, but initial model training and longer training sessions that 300 plus epochs should use them to reduce costs. It's worth noting that 300 plus epochs is actually the recommended length of training for initial training for a YOLOv5 model according to the docs. So if we were to actually have trained our model for the length that was recommended and then extended it further, we would have likely very quickly seen that the A100 was outperforming the A4000 in terms of cost benefit, but time constraints cause us to need to lower those values. Finally, I mentioned this briefly as being unaffected by adding more epochs, but accuracy is something that can and should always be considered when training a YOLOv5 model. And one of the reasons you should consider a data center GPU, specifically the A100, is that it can train more quickly with large batch sizes. And in our experiment, we actually used a batch size that was 6 times larger in the A100 than in the A4000, as the A4000 couldn't handle that much data at a single processing point. Smaller batch sizes have been shown to contribute to poor batch norm statistics overall. This is again per the YOLOv5 docs. So theoretically, a higher quality model could be obtained more easily when using a larger batch size that is afforded by a data center GPU. So without further ado, I would say my recommendation if you are training YOLOv5 for your own custom project would be to start off with a A4000 if you are using a smaller data set, or an A100 if you are working on a more computationally expensive task. You can't really go wrong. As should be noted, the RTX 4000 for 20 cents cheaper got nearly the same exact training cost. The training time was only about 1,000 seconds more. So there are a lot of situations where you may want to not use the recommendations I just gave. They're not always going to be the ideal. That being said, broadly speaking, judging by the benchmark experiments we performed today, the A4000 and the A100 would be my recommendations for the smaller model training and the more expensive model training, respectively. I want to say thank you really quick to everybody for attending. This has been a really fun session, fun putting together.